Today I'd like to tell you about our latest updates with the RIC Myoelectric arm. And I want to start by talking about our perspective for the project. It's based in part on a concept called a disruptive technology. And a disruptive technology is an interesting concept that the very traits that the mainstream market looks for are actually not what you want in a new product. You can create a product that has things that the mainstream audience would say, well, that's exactly what I don't want. And some examples of this are the Honda Super Cub, which was the first dirt bike application. And everyone looked at that and said, well, it's not as powerful as a Harley, it's not as strong, it doesn't look nice. But it had a very niche market that quickly grew into a large market, and Honda was able to deliver at a lower price point, and they quickly became really popular. Another one is the iPhone. It didn't have a keyboard, and if you looked at the people who were using smartphones at the time, they said it has to have a keyboard, otherwise I won't use it. But there was this whole untapped market for which Apple correctly saw that they could tap into that market without a keyboard, and then they could create a smaller device, they could give more screen space, and as we now know, it's quickly expanded. Now it's become the mainstream market, but it started out being an untapped market. So I'd like to apply that idea to the field of prostheses. If we think about it, most of us interact with end users, right? The people who actually use a prosthesis. And they come into our clinics, and typically they say they want more function. They want more speed, they want more torque, they want more degrees of freedom, they want more. And this is evidenced in surveys, it's pretty common. But how many of us talk with people who don't use a prosthesis? The people who reject the use of a prosthesis and say, actually, I've already got one good limb, that's good enough for me, what you have to offer isn't good enough for me. If you survey these people, you actually find they have a very divergent set of needs. And specifically, they want less weight, and they want something that's so small that it starts to look cosmesis. So this is a very divergent set of needs. And if we keep addressing the needs of the end users who are using devices, we're likely to miss a large segment of the population. Actually, only 50% of people typically use a prosthesis, so there's a big population out there that we could be tapping into. So based on our work talking with clinicians, we've found three main needs. One, the devices are too heavy to wear. These devices aren't connected to your bones. They're put on with a socket, so it's kind of like wearing a laptop bag all day. It gets heavy, and so it doesn't matter how fancy your device is, it doesn't matter how strong it is, it doesn't matter how many degrees of freedom it is, if it's sitting in your closet. In order to get a device that people can comfortably wear, the entire device and the socket should weigh less than the anatomical counterpart. The devices are also typically too large. They're often designed for 50th percentile males, which means they're too large for 72% of adults. And then there's minor issues like if the thumb, which is your base, is moving at the same time your fingers are moving, that makes prehension awkward. And we strongly believe that the wrist has a greater function and dexterity than individual fingers. So if you have to sacrifice something, it should be the fingers, individual finger movement, not the wrist. So our goal was to create a prosthesis that was a 25th percentile female in mass and size. That means if you lined up 100 females from the smallest to the tallest, this one would be the same size as the 25th smallest female. And that means that it'll fit 87% of adults and roughly 50% of teenagers. Should be cosmetic, and by cosmetic we mean noiseless, quiet, contoured, and natural. And then once we've hit those benchmarks, match the other benchmarks wherever possible, force, speed, etc., but only if we hit the size and the weight specifications. And finally, we wanted to create a smart device. We wanted to use pattern recognition, make a device that is intuitive to control. And so I'm going to start with the end. The engineers lived happily ever after. And so if you haven't seen a happy engineer before, this is a happy engineer. This is the day that we sent the device home with our first subject. So I'm happy to stand before you today and say the device is out of the engineering lab. It is in a field trial, it's being tested, and so it's a great day for the engineers. How did we get there? We definitely use iterative technologies. I'd like to think that they're disruptive. They're definitely different than what's typically done in the field. So we spent a lot of time optimizing the design and the efficiency of small gears. In this video, I'm showing you an example of a cycloid. So we spent a lot of time developing the analytical tools and theory of, how does a cycloid profile optimally work? What is the efficiency of a cycloid drive? And that allowed us to create really small transmissions that are still strong, high efficiency, so that we can hit those specifications of 25th percentile female while still providing a torque and speed specs that we need. We also developed really small motors that have high torque, high speed, and are designed specifically for application in prosthetics. And again, this allowed us to meet our specifications while not having to sacrifice speed and torque. So I thought it'd be interesting to show you a progression of how we got to the happy engineer phase. So this was our first completely put together arm, Alpha 2. Alpha 1, we were just developing components, testing out our new motor designs, testing out our new gear designs. But in Alpha 2, we actually started to put things together and realize where the interactions were going to cause us to have to re-evaluate our different technologies. Not a device you'd want to send home with a patient. So by Beta 1, it's starting to look like a real arm. It's looking pretty nice. There's still wires which you don't want, but you can start to see it's gonna work. So Beta 2, we actually put on several patients in a lab setting. You can see how small the device is in the picture on the right, and you can see we've tucked in all the wires, so there's no wires that are out at this point. And then finally, Beta 3, which is the device that we've now sent home in field trials, we've tightened up the form factor and made it look nice. So, what's under the hood? The fingers are not individually controllable. In order to get the weight down, we focused on having wrist movement, not finger movement, but the fingers do wrap around. And this is critical because we have a 25th percentile female hand. That means it's really small, but it has to hold normal-sized objects, which tend to be large. And so if you're going to get a small hand to move quickly and yet hold large objects, the fingers have to be able to wrap around. We have an independent thumb. That allows us to achieve a large number of grasps. Our wrist flexion is actually canted at an off-axis angle called the dart thrower's angle. And this, combined with wrist rotation, allows us to achieve 95% of the motions that the wrist does in daily life without the need for a separate actuator that does ABA deduction. And so by only having 2 motors instead of 3, we were able to get the weight down, but we didn't sacrifice anything functionally. We are using the universal quick disconnect, which means the hand is compatible with other hands, and likewise our arm is compatible with other hands. It has wrist rotation. The elbow flexion, again, has that kind of biomimetic canted angle, and that means that when you flex the elbow, the arm actually naturally moves towards the midline, towards your mouth, so that you can do feeding tasks, hygiene tasks, without the need for an extra actuator that does humeral rotation. It also has a very natural free swing, such that when you're walking it rotates very biomimetically, but this doesn't interfere with rigidity when you're trying to do tasks that require more rigidity. The entire prosthesis weighs 1,500 grams approximately, and that includes an extra degree of freedom. So this, compared with existing devices, which typically weigh more than 1,500 grams and don't even include wrist rotation, this is a really impressive goal. But we're not done yet. We really want to get down to 1,300 grams, which is our final goal. And we haven't really done weight optimization yet of our metal components, and that's our next step. One of our next steps is to get that weight down to 1,300 grams, which at this point, given how packaged up the design is a very that's a very doable goal. You can see the close time of the hand, pinch force. All of the specs are very comparable to existing devices. And actually the wrist is a whole lot faster and a whole lot stronger than anything commercially available. And we're really excited about that. Hand and the elbow are comparable with what's already out there. So at this point, we've had someone home for 4 weeks as part of a 3-phase study. And they've been doing really well. They've really liked the device. Their pre-take-home outcome measures are better than the conventional arm. using conventional control and equal to the conventional arm using pattern recognition control. Given that this device has 2 additional degrees of freedom, it's got a wrist flexor and it's got an independent thumb, I'm actually surprised and encouraged that they've been doing as well controlling this more complex device at home, day in, day out, than using a simpler device. So we're just at the start of our field trial, but we're really encouraged by these results. So the next steps are to finish up the field trial. We hope to get 10 subjects in that and then process the outcome measures. And then we're in the initial stages of commercializing the arm and the associated technology so that it can get out to end users and they can actually use it. As with many of our projects, this is a large group effort that includes electrical engineers, mechanical engineers, clinicians who are both giving us really valuable insight and also helping us validate the device and test the outcome measures, and couldn't be done without support from the Department of Defense. And with that, I'd be happy to take any questions.